Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on Gauss quadrature method or Gauss quadrature rule for numerical integration or numerically approximating a definite integral of f of x from a to b. And we said that we need to find some points which are called quadrature points xi to evaluate the function, and then we need to find some weights which are wi or quadrature weights. All right, and we said that we start by defining the problem of integrating over -1 to 1, and the reason is that when we do over -1 to 1 and applying the condition is that this approximation must give us exact result for polynomials from degree 0 to degree 2n-1. When we do over -1 to 1, we are actually able to find the exact solution for the quadrature points and the quadrature weights. And the quadrature points are the roots of the Legendre polynomial of degree n. So if I have n points, and we have n roots for the polynomial of degree n, and the weights are related to the quadrature points and the derivative of the Legendre polynomial by this equation. But we have to be careful because this equation is only valid when the Legendre polynomial is normalized, such that its value at 1 is equal to 1. Okay, I mean, for roots, the normalization doesn't matter because the roots don't really care about the actual coefficients, just the ratio of the coefficients. And this table from Wikipedia, we looked at the third 3-point quadrature rule and the 5-point quadrature rule in the previous lectures, and now we want to implement a general case where we specify the number of points we want to use, and then we find the weights and the quadrature points, and then calculate the integration. Now, in order to do that, we have to be able to find the Legendre polynomials and then find its roots and then the weights. All right, and so the first thing we need to do is see how we can find how to implement the Legendre polynomials. So Legendre polynomials are polynomials, right? And in the previous lectures, we already looked at how to implement polynomials in Java. And these are an orthogonal set of polynomials and are only defined over -1 to 1 interval. Okay? And over this -1 to 1 interval, they have this orthogonal property. Okay, -1 to 1 pn degree m degree n. If n is not equal to m, this has to always be 0. And I put 3 different definitions of the Legendre polynomials here. One is through the generating function. So Legendre polynomials are the coefficients of a series with t to the n, such that this series becomes equal to 1 over a square root of 1 minus 2xt plus t squared. And if you're familiar with the physics and you know that this type of function, square root of 1 over square root of 1 minus 2xt plus t squared, is a Newtonian potential or Coulomb potential in electrostatic or Newtonian gravity. This type of thing happens all the time, and then we can expand it using Legendre polynomials. Now, I mean, obviously this is not the best definition in terms of actually being able to calculate the Pn of x. So the other one is Bonnet's recursion formula. So if we start from P0, which is 1, and P1, which is just x, all right, and then the Pn plus 1 is times n plus 1 is 2n plus 1 x Pn minus n Pn minus 1 of x. So this is one definition. The other one is using Rodriguez formula, which is a more direct approach, right? It's not based on recursion. It's just x squared minus 1 to the power of n, okay? Take the nth derivative divided by 2 to the nth times n factorial. So we have to calculate the factorial, we have to calculate 2 to the n, and take the nth derivative of x squared minus 1 to the power of n. All right, so both of these recursions and the direct approach are easy to implement. So let's head to Eclipse, and we had in the previous lecture we had this project demo polynomials, and we implemented the polynomial class in Java based on the definitions that each polynomial has a degree integer, which is the degree, and an array of coefficients which has the length of degree plus 1, because we have to go from index 0 to index n, right? X to the 0th power to n to the nth power, so n plus 1 coefficients. And the most important thing was for us to implement the operator overloading for addition, subtraction, and multiplication and negation. And we also had some functions or methods such as toString, and then evaluate, and then which we implemented the most efficient way of evaluating a polynomial, which is Horner's method, and then compositional function, and then the roots. Roots are important here because for Legendre polynomials we want to find the roots. And then so one thing that we need to implement here, the first thing we need to implement is differentiation, public polynomial diff. All right, if we want to find the degree, so int degree diff is degree minus 1 when we differentiate a polynomial. And then when we differentiate, we have to create the coefs. So coefs diff new double, and here because we already know the degree here, plus 1, and then for int I equals 0, I less than coefs diff dot length I plus plus. Each coefficients for the derivative of a polynomial is its corresponding coefficients at index I. Okay, I plus 1. Remember, the 0th order coefficient, a constant term, has a derivative of 0, right? So we don't put it there. And the first term, the first order term, a1 times x becomes a1. a2 times x squared becomes 2a1 times x. So each one is multiplied by its corresponding degree, which is I. All right? Or I plus 1. So the ith term in the diff coefficient corresponds to I plus 1 term in the original derivative, because the first term is 0, right? The 0th term or the constant term of the diff is the first term. All right? And all right, and then we return a basically polynomial for the double coefficients, coefs diff. All right, and if we want to diff it with m times diff, this is just the mth derivative or nth derivative. Mth derivative. We just define a polynomial. Let's call this polynomial polydiff equals this. And then for int I equals 0, I less than m, I plus plus, we say that, okay, polydiff equals polydiff dot diff, and then return polydiff. So we make a copy of the original polynomial, and then we differentiate it, assign it to this previous one, so this just goes around like a loop. Okay, and then we return it. So let's go and test this. Okay, I'm going to create a new class here. test diff polynomial. Alright, so here I'm going to create a public static void test1, and I'm going to invoke test1 here in the main method, and then here I'm going to create a polynomial p1 or poly1, whatever you want to call it, new polynomial, and I'm going to say that okay, 1x 2x squared minus 3x cubed plus 4x to the fourth power. So I'm going to do a sysout on poly1. Let's see the result. 4x4 minus 3x3 plus 2x2 plus x plus 1. Alright, I could in fact have one of these equal to 0, doesn't matter. 1x 2x cubed 2x squared 0x cubed plus 4x4. Alright, and then let's test derivative. So polynomial poly1 diff is poly1 dot diff, and then sysout poly1 diff. So the one constant term in poly1 becomes 0, so we don't see it, and then 1x becomes 1, 2x squared becomes 4x, 3x 0x cubed becomes 0x squared, and then 4x4 becomes 16x cubed. And if we return this, let's say again I don't know, minus 1x cubed, 1 becomes 0, 1x becomes 1, 2x squared becomes 4x, 3 minus x cubed becomes minus 3x squared, 4x4 becomes 16x cubed. Alright, and sysout poly1 diff twice. So diff twice, basically this is the poly, this is diff 1, so maybe let's just poly equals, and then diff poly diff, and then twice diff diff. So so the poly is basically, okay, let me just hide this again, I'll comment this and run it. So what we see here is that again the differentiation works fine. Let's uncomment this. We are differentiating twice, so 1 becomes 0, 1x becomes 1, 2x squared becomes 4x, 3 minus x cubed becomes minus 3x squared, and 4x4 becomes 16x cubed. And then the second twice differentiating is basically differentiating the diff. Okay, so 1 becomes 0, 4x becomes 4, minus 3x squared becomes minus 6x, 16x cubed becomes 48x squared. So differentiation works. All right, now we're going to create in the polynomial, we're going to create a package called special, and in the special we're going to create a Legendre polynomial. In the Legendre polynomial, I'm going to use a static method, use static methods because there is no need to instantiate it. So a private constructor. Alright, so no instantiation and just a static method. So public static. Let's start with the recursion, right? So in the recursion, we have this Bonnet's recursion, right? So let's go with from Bonnet and int degree. So we have an int degree, public static. We're going to return a polynomial. Again, I typically don't recommend recursion because it has a cost, overhead cost of going into the method stack and then coming back up. So so from Bonnet, or maybe just let's call it Bonnet. And then, okay, let's keep the from. So from Bonnet, and we have the one thing that we have is the stop criteria and then the return. All right. So the stop condition is that if degree equals 0, we return 1. So remember, for Bonnet we need to have two, and these are two initial conditions. If degree equals 1, we return, and in order to be able to do operator overloading, I'm going to, from the polynomial class, if you recall, in the polynomial class we had a static field which was x, our base polynomial, which is 1 times x. So I'm going to import it as a static member, polynomial dot x. So 1 plus 0 times x, this automatically converts the thing into a polynomial. If degree is 1, we are going to return x, right? These are our stop conditions. If I go back, so p0 is 1, p1 is x. And then obviously we have to check that we can check that, or check that. So Legendre polynomials are basically defined between -1 to 1, but here we don't check that condition. We could check that condition at some point, but we don't have to. We can just and what do we do with this recursion? 2n plus 1 times x pn, so 2n plus 1, so return, maybe let's just also define n degree 2n plus 1, okay, times x times pn. So if I'm evaluating pn, this should be pn minus 1. All right, so the problem here is that if I put we have to actually, we're looking for pn, so n plus 1. So in my code, n plus 1 should be degree, so n should be degree minus 1. All right, let's keep that in mind, and then I can use exactly this formula: 2n plus 1 x pn minus n pn minus 1. 2n plus 1 x pn. So again, recursion means call the same method on n, and then minus n pn minus 1. N times call the same method n minus 1, and then once we find this thing, we divide it by n plus 1. N plus 1. All right, that's how recursion works. And then I can go back to test div and create another test, test 2, and then test 2, I'm going to invoke test2, and here I'm going to create a polynomial, and so what we could, two things we could do. So this we could create this as a extended polynomial class, but we decided to go with this kind of like helper class or with static methods. But in fact, we could actually extend the polynomial class, but the problem was that then we had to do one of these we have to invoke one of these two constructors as the super constructor. So let's stay with this. All right, so here in test2 I'm going to say that polynomial Legendre equals Legendre polynomial from Bonnet degree 0. Maybe let's just do the sys out on it. So Legendre 0, 1, 2. So we already know that 1 and 2, 0 and 1 should be 1 and x, and the second one is 1.5 x squared plus 0x minus 5. 3, 4, 5, 6. 3, 4, 5, 6. All right, and what I'm going to do here, let's copy these and then bring it back to our PowerPoint. So let's go to here. I have plotted some of the functions, some of the polynomials. P0 is this green, which is 1. P1 is this one, a linear. P2 is this one, a quadratic. P3 is this blue one, cubic. P4 is this pink one, and P5 is this red one. And let's compare the results. P0 is 1, right? P1 is x, this coefficient is 0. P2 is 3 over 2, 1.5 x squared minus 0.5, yes. P3 is 2.5 x cubed, this coefficient is 0, minus 1.5 x, right? P4 is 35 over 8, which is 4.375. x4 minus 30 over 8, which is 15 over 4, which is 3.75. x squared 3 over 8 is 375, right? So it's correct, and we can go on, and all these are correct. So our code is working fine. So that's one way of calculating the Legendre. The other one is from Rodriguez direct equation. So public static polynomial from Rodriguez. How do we write it? From Rodriguez, again int degree. All right, here let's just so what we need to do first, we need to calculate x squared minus 1 to the power of n. This is our polynomial, and in order to do that, we have to be able to create a polynomial x squared minus 1 and raise it to the power of n. Okay, so let's and then so step 1, create this. Step 2 is to dn dxn, so nth derivative of x squared minus 1 to the n, right? Nth derivative of x squared minus 1 to the nth power, and then 2n n factorial. Step 3 is 2 to the n times n factorial, so we have to be able to also calculate factorial. Alright, so let's go to our polynomial class, and here we implemented diff, but we need to also implement power, public polynomial pov, and then int m. So we want to be able to take our polynomial p of x and raise it to the power of n. So we have to be able to basically multiply it m times. So again, you already know the drill. Polymult equals this. We start with a copy for int I equals 0, I less than m, I plus plus, polymult equals polymult times polymult, right? We multiplied n times. So the first step, it gives us p squared, and then we substitute it there. Okay, we have to actually multiply it by this. So the first step is this polynomial, and then we multiply it by itself. It gives us this squared, and then multiplied by this again, it gives us this cube, and etc. And then return polymult or polypov or whatever we can call it. And let's go back here and try to test it. Public static void test3, and we are going to invoke test3, and here in test3 what I'm going to do is basically create a polynomial, let's say a simple polynomial, x squared minus 1 and then x minus 1 0x x squared. So let's do a sysout on poly 1. Maybe let's just first create something simpler like x, and then boom 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 pov like 2, pov like 3, and pov 4. Okay, so we have x, we have x cubed, so what happens here is that I believe we shouldn't start from this, or if we start from this we should reduce the order by 1, right? Because if m is 1, power of 1, if I keep this like this, if m is 1, it means it's power of 1, so it should return this, but here I'm getting this squared, so I have to yeah, so this makes sense. If m is 1, we never go through this loop. If m is 2, we only do this loop for once. Okay, now this should work. Yes, so x squared, x cubed, and x to the 4th. That's correct. So see, the problem here is that it's actually increasing the order, right? And that's not good. So we can right now we don't care that much about this, but what we can do here is we write a method called let's public double public polynomial reduce coefs. So what this does, it starts to remove the zeros from the trailing coefficients, remove zeros from higher order terms. So we create a double reduced coefs, and then basically what we can do here is we start with an index equals 0, or maybe degree. So if we have the coefficient array goes from 0 to degree, so we start with degree, and then for int I equals and we can say while math.abs coefs index is greater than or less than 1 in negative 9, that's our, or minus 1 in negative 10, that's our threshold for 0. Then we're going to index minus minus. So what happens here, we start with the last term and check whether or not this coefficient is pretty much 0. And again, because we're using double numbers, we cannot do the exact equality. That's not recommended. If it's 0, I increase the index and I go all the way until I hit the first non-zero term, okay? And once I do that, what I do is I have the index, and then now that I have that, I created an array of reduced coefs, which is new. Now I know the degree, right? From 8, for example, here I go to 4. A new double, it's just coefs or degree minus index. Actually, it's just index, right? Eight, 7, 6, 5, 4. So the first index is the degree of the reduced polynomial, and then return new polynomial with these new reduced coefs. Okay? And now here, what I'm going to do here, when we do the diff, for example, I return the polydiff time dot reduce coefs. And when I do diff, I also return. Alright, before that, let's go and try the reduce. So public static void test4, and here I define this polynomial, and then let's do a sysout on poly1. We're going to invoke test4. X squared plus x plus 0, okay? And now let's do a sysout on the poly1 dot reduce coefs. It just says 0. And that's a bit odd. That's because we didn't, okay, so for int we didn't assign the coefficient, there's just 0. For int I equals 0, I less than index I plus plus, I actually equal to index, right? And so index is the new degree, so this should be degree plus 1, and reduce coefs dot length or index plus 1 I plus plus reduce coefs I is equals coefs I. All right, now we assign them. Let's do the semicolon, and let's just refactor, rename it to just reduce. Okay, so now we have we don't have the x squared anymore, we only have x, so it works. Let's see, 0 minus 1 for example, so we have minus x squared. It shouldn't do anything wrong. Yeah, it's the same thing. X squared 0x cubed 2x to the 4th, right? But let's say this was actually 0, so I don't have an actually 3 x to the 4 or x to the 3 term, so this should already reduce the coefficients for me. That's correct. So I don't get these two terms anymore. So the reduce is working. Now in the polynomial, in the diff, when I do the diff, I return the reduced version. Actually, it's a good idea to return the reduced version in all the methods. And so even in the pub, I return the reduce. Okay, so now if I go back here and then invoke invoke test 3, which is power to the increasing to the powers. Now the original poly is 0x squared plus x plus 0, so it's only x, right? This p of x equals x, and then power 2 is x squared 0x0, power 3 is x cubed 0x squared 0x0, and power 4 is x4 and x cubed 0x cubed 0x2 0x0. So that works, and all of these are reduced nicely. All right, and let's go back here. So we want to calculate so we create a polynomial. Let's call this the base is x times x minus 1 to the power of degree. All right, and then let's diff it. Polynomial diff base is base diff degree times. Okay, and then finally we need to calculate 2 to the nth times factorial. In order to do that, I'm going to use the function factorial that I wrote in my math utils class. And remember that factorial in general should return an integer or long, but here I'm returning a double. The reason is that then it allows me to hold more digits, more precision. All right, so I'm going to give a dependency, which I think it already has a dependency on the math util. Yes, mathlib. So double coef is math.pow 2 to the degree times math utils dot factorial. We can take a double value and return a double value and its degree. All right, and eventually return the result. So eventually we're going to return coef times diff base. Alright, so let's go here and let's copy test 2 and test 5. We're going to invoke test 5, and here I'm going to do a sysout on bonnet. So the first one is bonnet, and maybe let's also when we do this, let's also try to reduce it, dot reduce, and we could also do that here. Actually it doesn't really, okay, it doesn't matter. And then do exact same thing from Rodriguez from Rodriguez let's run. All right, let's see. 1 from Rodriguez we get x squared minus 1. So Rodriguez is seemingly is not working. The question is why, and the answer is because we are multiplying by coef instead of dividing by coef. So let's multiply it by 1 over coef, or just divide it by coef. So the coefficients are so the Rodriguez why are we getting the 0th term? That's because if degree is 0. Okay, so we have to go here in the powering. If m equals 0, we're going to return 1 plus 0, basically 0 times x, constant poly, right? P of x equals 1. We're going to just return 1. We could actually, okay, yeah, for m1 okay, so the problem I guess with powering is 0, and the same thing with diff. So what diff is fine, because if m is 0 we never go through this loop, so we end up with the same polynomial, right? So this should work now. Yeah, so we end up with 1, and in the bonnet we could also reduce the polynomial. Let's call this the result, and then we just say okay, return result after reducing the coefficients. All right, 0x plus 1, 1x, 1.5x squared, 0x minus 5, and all the way to the 6th degree, which are exactly identical. All right, so this was the introduction on how to calculate the Legendre polynomial. Now that we have the Legendre polynomial, it's very easy to implement the general case of Gauss quadrature, which will be the subject of the next tutorial. Thank you for watching, and I'll see you in the next video.